baik yang offline maupun online. Kesempatan hari ini kita kedatangan pembicara, yaitu Profesor Bartlomiej Czech, atau beliau juga bisa dipanggil Prof. Bartek in short. Dia dari Institute of Advanced Study Tsinghua University in China. Dan sedikit background mengenai Prof. Bartek ini, dia lulus dari S1 di Harvard University itu 2 tahun sebelum Stella University. Dan sebagai informasi, beliau adalah suami dari Prof. Oke, itu. Lalu beliau melanjutkan ke kata.
Saya iri ya, karena dia kalau ada yang perkenalkan Prof. Stella, nggak ada pernah yang bilang dia sebetulnya istri Prof. Bartek ya.
Jadi pejabat dulu, Prof. Jadi pejabat dulu baru diperkenalkan Stellanya sebagai. Baik, lalu melanjutkan ke Tata Institute. Lalu dia menyelesaikan S3 di University Pennsylvania dengan supervisor Vijay Balasubramanian. Nah, ini menarik sekali karena Vijay juga dia itu ada kaitan dengan Indonesia karena dia menghabiskan sebagai masa kecilnya 2 tahun, 4 tahun
dia tinggal 2 tahun
di Jakarta. Dan nanti kita lihat setelah kemudian beliau pernah postdoc di British Columbia, lalu juga di Amsterdam. Ini 2 tahun setelah saya lulus juga. Jadi kita tidak sempat bertemu di Amsterdam. Lalu melanjutkan di Stanford dan sempat juga di IAS Princeton University. Baik, ya tanpa berpanjang lebar lagi, Prof. Bartek akan mempresentasikan mengenai which quantum set can describe geometries, dan presentasinya sekitar 1 jam. Lalu kita masuk sesi tanya jawab itu setengah jam. Tapi mungkin kalau waktu lebih ya maksimal 2 jam. Dan mungkin untuk presentasinya dalam bahasa Inggris, tapi sebagai informasi kalau ingin bertanya silakan juga bahasa Indonesia karena tadi sudah melihat beliau bisa berbahasa Indonesia dengan lancar. Baik, waktu yang tepat dipersilakan.
Terima kasih. Sebentar lagi bahasa Inggris, tapi pertama-tama sangat terima kasih untuk hormat besar buat saya bisa kasih talk di sini. Dan saya sangat berterima kasih untuk bisa kenalkan semuanya. Dan ya, kalau ada pertanyaan, kalau ada yang mau bertanya sesuatu dengan bahasa Indonesia, silakan, saya mengerti dan mungkin saya akan menjawab pakai bahasa Inggris, tapi begitu kita bisa saling mengerti pasti. Dan yeah, so now I will switch to my English mode because in English the talk will be better and you want good quality from me. So, okay, the title that I gave you was something about which quantum states can describe space-time geometries, a topological perspective. And I gave this title because I wanted you to know what you are coming to hear before you come here. But when I give this talk in conferences where people already know what we're talking about, which is about space-time geometries and quantum mechanics, then I give another title for people who already know. And this is the title that I give, which is Everything Everywhere All at Once. And so this, I mean, maybe this movie came with a different title in Indonesia, but this is a movie that was in cinemas last year. So, and the reason why I give this title is that this subject really combines literally, I mean, not everything, but it combines so many different things. And some of them are listed here in this longer title. So if we are lucky, we will be able to talk about all of these concepts today. And before I really start, I have to acknowledge my collaborators. So this is my postdoc and my student and my undergraduate student who just got into a PhD at MIT. So he just started at MIT last September. And now we're I should start with this slide, but before that, I will talk for maybe 5 or 10 minutes about the background for this. That's why we did the survey in the beginning. And the most important thing that I want to talk about is tensor network states, because this whole talk is really about tensor network states. Also, as I understand it, a lot of people here study various aspects of quantum physics, but not necessarily about space-time. So maybe you care about quantum states more than about gravity. And so let me spend a few moments to talk about that. So suppose that you have some state of a quantum state of n qubits. For example, like a state that could be, for example, the ground state of an Ising model or something like that. But you have many qubits and you have n qubits. So a general wave function, so I will write n here for n qubits. And the general wave function of such a state would be written in what form? So I will try to write down a wave function now. Well, we have to, first of all, there are these partial, we have to write down a basis of states, and then we express the wave function in some basis. What are the basis elements? Well, a basis element would be, for example, plus, let's suppose that we measure those spins along some axis, like the z-axis, and they come up or down. I will denote them as plus or minus. Maybe we measure them along the x-axis, so then the usual notation is plus and minus. So a basis vector would be one spin is plus, another one is minus, another one is minus. A sequence of pluses and minuses, n of them, would be one basis state, yes? So one of them could look like this, for example, and there are n of them. But in general, the full wave function will be a combination of all of those things. So what I should really do here is I should write some kind of S1, S2, S3 for the spin of the given qubit up to the nth qubit, yes? And this is a given, this is just a single basis element. And now the full wave function is going to combine, is going to be a sum over all possible values of those spins, S1, S3, all the way to Sn. They can take values plus or minus. And then each one of these basis states comes with some coefficient, yes? So I will write here a coefficient, psi, S1, S2, all the way to Sn, yes? And what I wrote here, I haven't done anything in terms of real physics. I just set up some notation which allows us to express the full wave function of a system of n qubits. Is everyone on the same page with me or not? Yeah. Okay, so now the first question is, how many different pieces of data do I have here? And the answer is, how many? Actually, let me have it from you. You tell me. 2 to the n, yes? Okay. So what we have is exponentially many pieces of data that have to describe for us this single wave function. And exponential scaling is really bad if you want to really do some physics in an efficient way. And so this is where tensor networks come in with their first motivation. So the first motivation for a tensor network, for the idea of a tensor network, is maybe we can find a more efficient description of wave functions of things like this that would not involve exponentially many pieces of data, but something that scales either polynomially or at most logarithmically with the number of spins, yes? So how do we do it? So to do it, and by the way, this is not, tensor networks are not guaranteed to be a successful method for describing everything exactly, because it's impossible. You can't have something which has exponentially large complexity. There are exponentially many possible wave functions here. You cannot just say, oh, a polynomial amount of data is going to capture everything about this exponentially large set of possibilities exactly. That won't happen. But it could be that these polynomially large descriptions of the wave function are rich enough so that they capture the wave functions, not exactly, but to a very good approximation. And that's what we want, yes? So we want something that will be a very efficient way of describing exponentially large pieces of data. Maybe the description will be polynomial in size, and it's not going to be perfect, but hopefully it will be really good. And so that's really what tensor networks do for us in this context. So for this, to do them, we invent a notation, and the notation is a graphical notation. So we start by saying that what's a single line? And the answer is that a single line, we treat it as a vector, which has a single index, like I, yes? So in general, in the future, I will not be writing those indices, but in the beginning, let me write an index, yes? So now, how about, and every time I have a dot here, the dot is, this is why we're talking about tensor networks, a dot represents a tensor that has as many indices as there are lines coming out of that tensor. So in this case, this is a tensor that has a single index, and a tensor with one index is called a vector, yes? Okay, what about this kind of stuff, yes? So here I'm going to have some kind of I and j, yes? And that would be naturally a tensor that has two indices. If I want to, I could write one of these indices at the bottom and the other one at the top, and then it looks like a matrix, yes? It's a matrix which, we usually think of a matrix as something which is a map that takes one vector space to another vector space. Here, it might be something that takes a vector that has a j index and takes it into a vector that has an I index, yes? Now, we would like to be able to say that this guy, if it acts on something that has a j vector, that has a j index, then that something would become a new vector, yes? The matrix takes a vector into a new vector. So we would like to be able to say that mji contracted with some wj is a new index, is a new vector called vi, yes? So we would like to be able to write this kind of matrix equation, yes? A matrix acting on a vector gives me another vector. Well, this is a matrix, and we already know what a vector is. This is a vector. And this will give us a new vector. So this kind of thing, we would draw in the following way. Here is our wj. It is acted on by a matrix, which is mji, and this whole object still looks like this. Now it's a new vector. Does that make sense? So what you have learned here is that when I take a line and I combine it with this another line and I join them, then this is like matrix multiplication. Now, another thing you can ask is, how about this? What is that? So you should be able to tell me what this is. Yeah. This is a scalar product, exactly. So this could be our wj, this could be a vi, and basically this thing here is like an inner product, yes? So it's something like wj, vi, and generally I would put here delta ji or a scalar product. I could imagine that this thing represents some other scalar product as well if I wanted to. So just one last thing as an exercise. How about this thing? This thing would be a tensor that has 3 different indices, yes? And so you can imagine that having tensors that have 3 different indices, for example, I could call it, let's call this S. I could call it MSIJ. This is a matrix on the IJ indices, but the matrix depends on the state of another leg, yes, which is the S. Yeah? So that's a 3-leg tensor, which could be useful for all kinds of practical purposes. Now, one example for how you can use it is you can construct things called matrix product states. What is a matrix product state? Let me draw it for you over here using just this piece of notation. Okay. So a matrix product state is something that looks like this. I take the object that I had over there, and I just connect it over and over, either on an infinite line, or maybe I can make a ring. Yes. Now, these are the indices that are always connected, so they're always multiplied by each other. If I formed a closed loop here, what would that be? It's a closed sequence of matrices with delta functions, like this, yeah? So what would that be? Imagine writing an expression of the form matrix Ij, matrix KL, matrix LM, NO, yes? And then you would have delta functions in between them that connect all the indices. What would that be called? That would be called a trace of all of those matrices. But this is a trace of a bunch of matrices, each of which depends on the value of this S1, S2, S3, and so on, right? There is an S here which determines what matrix you have, yes? So this kind of state here describes for us a wave function of a bunch of spins such that the amplitude for every basis vector is given by a trace of the corresponding matrices. So for example, so to be explicit here, for example, if I have, suppose that I put a plus, minus, plus, and minus, plus, and minus here, then we would say plus, minus, plus, minus, plus, minus, inner product with our wave function. So now we're taking a coefficient of this specific basis vector is equal to the trace of m of plus, m of minus, and I won't be able to write any further, but you know what it is. It should be m plus and minus. So the inner product are given by traces of the corresponding matrices. This something is called the matrix product state, because we're taking products of matrices before we take a trace, and that computes a wave function for us. So what I just gave you is a summary of the technique called called tensor networks. These are tensors, all of them. And it's a technique for efficiently describing wave functions. Is everyone okay with what I said so far? Are there any questions or comments? So it turns out that if you have I'm going to say one more thing about tensor networks in the way of, no, I'll say two more things about tensor network states in the way of a motivation for the talk, and then we'll go to the actual talk. Yes. So the next thing I wanted to say is that I introduced tensor network states with the idea that they will allow us to describe wave functions of large systems, maybe n-qubit systems, where n is a scaling parameter, in an efficient way. I haven't told you yet just how efficient is it, yes? So, well, it depends on the problem that you have on mind, but one problem that you may want to solve is, how do I describe the wave function of a critical system? For example, a critical Ising model in 1+1 dimension. This is the most sort of standard example of a system that has you take this Ising model, spins in some magnetic field, and you tune the magnetic field to just the point where there's criticality. And criticality means that correlation functions between spins are scaled are not exponentially suppressed, but they have power law behavior. Yes, so this is criticality. How do you describe such a thing if you have the wave function of those spins? If you're in a system that's not infinite, but maybe it has like 1,000,000 spins, like how would you describe such a wave function? And how do you do computations in it? And so this is where tensor networks become really useful. It turns out that because of criticality, critical systems are often described or almost always described by what's called conformal field theories. The conformal in a conformal field theory means that there is no scale. And because there is no scale in the problem, therefore correlation functions are not exponentially suppressed by power law. Why are they not exponentially suppressed? Because if you have exponential suppression, then your correlation functions would have to look like, this doesn't work anymore, would have to look like exponential to minus, let's say a 2-point function. There is some kind of x0 minus x1, but this thing has dimensions, yes? So in order to have exponentially dying, thank you, in order to have exponentially suppressed correlation functions, you would have to put something over here, some kind of mu, yes? Which tells you the width of that decay. Well, that's already a scale, yes? So every time you have a typical theory, like a typical quantum field theory, correlation functions depend on distances exponentially, but to make an exponential, I always need a scale there. A conformal field theory is a field theory where correlation functions, is a field theory where there is no scale. So there can't be an exponential dependence of correlation functions. So instead, what happens is what? Instead, we have polynomial, like we have power law dependencies of correlation functions. And so that's what the conformal field theory is. So criticality, if a system is critical, that means that maybe we started from a theory that had some scale, but then we flew down the renormalization group flow to a point where that scale doesn't matter anymore. So the flow sort of forgot about the scale because that's one way of thinking about what a conformal field theory is. And so criticality is where a scale becomes irrelevant, and we have a description of a critical system as one there is no scale, there are no exponential behaviors, only power law-like behaviors, and those systems tend to be the most interesting, I mean, for many purposes, the most interesting systems to study. Now, how would you describe such a wave function? I talked about tensor network states. We should use a tensor network. So you can ask me, what kind of tensor network is going to be, is there some special design of a tensor network that is particularly good for describing wave functions of conformal field theories? Maybe this thing works. This is a matrix product state. I gave you one example. Well, it turns out that this is not a very good description. This thing actually has correlation functions that are like that, and this new parameter has to do with what sits in those tensors in detail. So instead, we call it architecture. A different architecture of a tensor network state is ideal for describing conformal field theories. And let me draw that architecture for you right now. So, and we're going to, just like here, every time we have a free index, like those actual spins, then we draw free legs, yes, like this. And then what we're going to do is we're going to alternately make little three-legged tensors over here, and then we will combine these things using four-legged tensors like this. Okay. And now we will again combine. Imagine there's another guy coming here, which combines. And so I have a three-legged tensor, then I have a four-legged tensor, then I have a layer of three-legged tensors, then I will have another layer of four-legged tensors one more time. And then I will have another layer of three-legged tensors, and so on. Does that make sense? So think about the complexity of this thing. This complexity is like, there is some layer whose complexity is linear with the size of the system. But then I have another one which is half as big, and another half as big, and half as big. If I combine them all together, this will be a convergent series which will converge to something which is again polynomial in the size of the system, not even logarithmic. And so this is definitely a very efficient way of describing a wave function if it works. Like I just told you, we counted how many things there are, and this goes linear with the number of spins. Much better than this, where we had exponentially many pieces of data to remember, yes? So the statement is that this tensor network turns out to be an exquisitely good description of a wave function of a conformal field theory. Wave functions of conformal field theories are, actually, that's a general statement. Wave functions of ground states of 1 + 1 dimensional conformal field theories, so of critical systems in one dimension, are extremely well described by this wave function, by this tensor network. Even though it only has linearly many pieces in it, whereas that thing had exponentially. So we in some sense managed to compress the exponentially many data that describe the exact wave function into something that just goes linearly with the size of the system. So that's the power of tensor networks. Now you can ask, why is it that we were able to do it? It's like compressing a file. I give you a file with a movie, maybe it has 100 megabytes in it, but if you press compressed, it will come out with like 1 megabyte. Yes, that definitely can happen. And you can say like, why is it? Clearly there were a lot of redundancies in this. in the initial file, so we were able to compress it without losing quality. Here we lose a little bit of quality, but only a little bit. So that's the idea of what tensor networks are. And now you know what tensor networks are as a general method, and at least one example of a tensor network that is useful. Okay, are there any questions about the tensor network? Yeah, primary. Why is there a for?
Yeah, why do we need the for like?
Yeah, if we didn't have the for-like tensors, then things would just combine, and it turns out that that would just make a tree. There would be no loops here. It turns out that these loops make things. There's a loop here, there's a loop here, and there's one big loop here. Yes. It turns out that loops make it a lot more efficient for some reason that is kind of hard to explain. Yeah. Any good question? Any other questions? Yeah.
Apart dengan spesifikasi wave function dengan matriks dari matriks lebih efisien.
Oh, we need efficient, but it's efficient for a different problem. So it turns out that when you compute correlation functions in this thing, they behave like those exponentials that I raised a moment ago. So this system is not critical. It still has a scale. That wave function doesn't have any scale anymore. So it's good, but just actually matrix product states are very useful. So this is also useful. It's just useful for different purposes. But if we want a conformal field theory, a description of a system at criticality, then we'll use this and not that. So this wave function is called MERA, for multi-entanglement renormalization ansatz. It was invented by a guy called Ifra Vidal from Spain, who is my good friend. And also, after he invented this, he decided that he's the guy to boss and lucky, and he now works for Google on quantum computing, actually, for them. Anyway, it's there's one thing that I didn't tell you about, which is actually very important, which is that when I said that this thing is a vector, I didn't say what is the dimension of the Hilbert space where this vector lives. So this leg, it could represent something that's a vector in 2 dimensions. It could represent something that's like a vector in 100 dimensions. Yes. So every time I draw a picture like this, there is always extra data where I'm not telling you what is the dimension that comes over here. Yes, on every leg. And if it's an exterior leg, like the spin, then we know what the dimension is because it describes the spin. So it must be a 2-dimensional leg. But if it's an interior leg, then we don't know what it is. Yes, it could be anything. So in general, what happens is that if you give me an exact wave function and you ask me, try to model it using this, and I say, but can I change the dimension that's inside here? And you say yes. So what I'm going to do is every time I have an interior leg here, I'm going to change the bond dimension to make it larger and larger and ask the computer, given that you have a 5-dimensional Hilbert space to play with, the interior one, because everything is contracted, so we don't see it on the outside, what happens on this leg. Given that you have a 5-dimensional interior leg, or maybe 7, 10, 100, yes? Can you make approximations better and better? And the answer is yes. So basically what happens is that if you allow this bond dimension to be as large as you want, then this description will be exact. But there's no point because we're trying to use it as an approximation scheme. If you say, make an approximation, but your approximation can be as complicated as you want, that's not even an approximation anymore. So in some sense it sort of doesn't make sense to make it very large, but there is a limit in which we can imagine making this as large as we want to, and then this thing would be exact. Okay, and for a conformal field theory, I can give you a more precise answer to the question what we lose. We generally lose data about the higher, about fields with higher conformal dimensions. But I don't want to get into this because I have a feeling that a lot of people here haven't even studied conformal field theory, so it will become too technical to really answer the question. But anyway, so that's tensor network states. Okay, so Now, the reason, this is not the only reason why tensor network states are interesting. In fact, tensor network states are probably most relevant and most interesting for people who study condensed matter theory. Because in there, we want to describe some complex system, which is maybe on your tabletop, yes? And but you really want to be able to compute something that involves 100 spins or 1,000 spins. That kind of thing happens a lot in condensed matter theory. And so maybe for condensed matter theorists, tensor network states are most useful. But for me personally, the reason why I came along to study tensor network states is that I studied the ADS-CFT correspondence. So a duality between a conformal field theory, we already talked a little bit about what a conformal field theory is, a description of critical systems with no scale in it. And it turns out that some conformal field theories have a dual description, or they automatically also describe gravity in one more direction. And so there is a duality between gravitational theories in D+1 dimension and conformal field theories in D dimension. Not every theory of gravity enjoys such a duality, but if you have gravity in what's called anti-de Sitter boundary conditions, and it's either Einstein gravity, like we know from general relativity, or something that's or maybe it's a theory of gravity that's closely related to Einstein's gravity, then there is such a duality. Now, because we have, in general, if I ask you, do we know what quantum gravity is? You should answer no. This is something that we're trying to study very hard. And we haven't found a good theory of gravity, quantum gravity, that really works. But ADS-CFT is an exception. That's a very special case where we know exactly what quantum theory of gravity is. Why? Because it is dual to a conformal field theory. And a conformal field theory we can study very well. Now, maybe you can see why I would be interested in tensor network states. Because of all of those, I mean, we've been trying to find a quantum theory of gravity. We haven't really found one that properly works in all circumstances, but there is one special case where we know what it is, and it happens to have a description in terms of a conformal field theory. But a conformal field theory happens to have a description in terms of this tensor network. So basically, this thing holds the answer to the question, what is quantum gravity in some special case? Not in general, but in some special case. So we should study that case very well, yes? Now, a key thing about the ADS-CFT correspondence is that the conformal field theory lives in some dimension, but the gravity side lives in one extra dimension, yes? You can sort of see it on this picture here. Suppose that I'm describing spins that live in one dimension. Here's the line, yes, it's a one-dimensional line. But the description of the full system is two-dimensional. So there's an extra dimension that has to do with, that I need in order to properly describe this wave function, yes? That extra dimension is the extra dimension that we have on the gravity side of the duality. There's more that we can see from this picture. One thing is that, look, here the spins are very closely spaced. What if I took this wave function and I cut it over here? Like I just dropped this part of the wave function. Then I would have something that looks identical as before. This thing is similar to that thing, but it's similar at the scale that changed. This scale became this scale. And if we go one level higher, then it will become this scale, this scale, this scale, and then this scale, yes? And so as I go higher here, I'm going to scales that are coarser and coarser. As I go lower, I go to scales which are finer and finer. From the CFT point of view, this is the ultraviolet, and this is the infrared of the theory. And this picture here gives me a graphical representation of what is UV and what is IR. Now in gravity, we have the same thing. There is we describe a gravitational system, and we say, oh, this gravitational system, if it has ADS boundary conditions, then it is dual to a conformal field theory. This gravitational system could have like some set of scales and another set of scales. And another, no, maybe I should say it the other way around. The conformal field theory that describes gravity, it consists of many different scales which are related to each other by a symmetry. And the more UV scales correspond to things on the gravity side, which are very far away from us, whereas the things that are near from us, from me here, are described by the infrared description of the CFT. So in fact, the ADS-CFT correspondence is a duality that exchanges UV and IR. What is ultraviolet from the CFT point of view becomes large scale from the gravity point of view, and what is infrared in the CFT becomes UV, very localized from the gravity point of view. So we have learned a lot of things just by looking at this picture, and this is why tensor networks are so useful, at least as a toy model of the ADS-CFT correspondence, because they make us see how such a duality as ADS-CFT might work. And I remind you, this is basically the only model of quantum gravity that we have that really works. So we had better study it well to learn as much as we can about quantum gravity. So that's my motivation for tensor networks. But if somebody here studies condensed matter theory, then you will have your own motivation. In general, tensor networks are an extremely important tool for many physicists. Okay, so now there is so now I'm kind of ready to get to the real talk, except that I realize that I've already talked for 35 minutes, but it's okay. So we'll get through like some part of it. I'll just give you a sense of what happens. So I have to tell you one more thing about the ADS-CFT. So I said ADS and CFT are related by a duality. If I want to study quantum gravity in ADS boundary conditions, I can just study conformal field theory. Very good. So the ADS boundary conditions imply that a space-time, yes, that is the object of study in gravity, in Einstein gravity, can be drawn as a cylinder. I don't have time to tell you about it in detail, but it just really looks like a cylinder over here. And then the conformal field theory that describes it in a dual way is I remember it lives in one less dimension, yes? Like if gravity is two-dimensional, then the CFT is one-dimensional, yes? So it lives in one less dimension. Where is that one less dimensional locus that describes the ADS gravity? It's on the boundary. So ADS is a solid cylinder, whereas like this microphone, whereas the CFT is like the empty cylinder. It's really the plastic on the outside of the microphone. Okay. So here's the next key thing. So, okay, and the whole thing about trying to study quantum gravity in ADS-CFT is to know how to translate questions about gravity into the language of the CFT, or vice versa. If we know how to translate from one side to the other side, then we can answer any question we want, in principle. So a lot of people, including my advisor, Vijay Balasubramanian, the reason why he became a professor at all is that he wrote one of the most important papers in the early days of the ADS-CFT correspondence, which described how to define in gravity the object that in the conformal field theory becomes the stress energy tensor. Before him, people didn't know how to write down the stress energy tensor for the conformal field theory in ADS-CFT, and he found it. That was the paper that gave him the job. And honestly, I also wrote, the reason why I'm a professor now and not doing something else is that I wrote a rather influential paper that also gives us tells us something about ADS and CFT are related. And that's actually differential entropy, which we talked about today. So that was really the most important contribution that I have made in my career so far. And but in general, a lot of people work on trying to understand how ADS is related to CFT and vice versa. And so here is probably the most amazing piece of that dictionary, of the translation dictionary. It's called the Ryuta-Kayanagi proposal, and from 2006, so it's almost 20 years old now. And Ryuta-Kayanagi realized that you can, so first of all, the vertical direction in the cylinder is time. So we can look at the quantum state of the CFT at one equal time slice. So this here is so what I'm drawing with my finger now is where you would have the wave function of the conformal field theory at one particular time. This is time, that's one particular time. That's where the wave function lives. That object that we have over here is basically supposed to describe the quantum state that lives here. And look at it. Don't you see that this picture kind of looks similar to that picture? So that gives the idea that maybe the reason why we have an ADS-CFT correspondence is that those quantum states have a tensor network-like description, and ADS is the tensor network. Maybe gravity is one big tensor network. That would be the reason to study it. Okay. So Ryuta Kayanagi said, let me take a subset, not the full system in the conformal field there on the boundary. Not the full thing, but let me take one particular thing, like a subset of those spins, yes? So not all of them. It could be like this subset, okay? Just some finite subset of them, of the degrees of freedom that live in the conformal field there. And compute a quantity called entanglement entropy. Oh, I didn't ask you. How many people know what the reduced density matrix is? Raise your hand. And how many people know what entanglement entropy, otherwise called von Neumann entropy of a quantum state is? Oh, I have like 1, 2, 3, 4, 4.5 hands. Yes, 4 people and a half. Okay. So okay. So then I think if we talk about this, then we will totally run out of time. But maybe it's worth it. It's probably more interesting than the actual talk. So let's do that. So suppose that you have a. Are people aware of the difference between a pure state and a mixed state? Yes. Okay. So suppose that you have a pure state, like we have been describing pure states over there, but it's a pure state on a large set of, on the full universe, yes? Right. So here's a description of a pure state. Typically what we do in experiments is that we compute expectation values of some operators, like O, yes, that's what we do. Now, suppose that, like I'm gonna draw this system kind of in parallel to what we have over here. This is a description of a quantum state at a particular time. And suppose that I divide it into 2 pieces. This piece will be called lab, okay? This is Bryn, and this is the rest of the universe, okay? Now, when we do an experiment, we only do it here and now, and not everywhere, yes? So the expectation, the kinds of correlation functions that we compute are correlation functions of operators that don't have arbitrary structure. Instead, if I took this observable that we really use in real life in an experiment done at Bryn, then it would have a structure of the form O lab tensor identity elsewhere, yes? In other words, it's an operator that acts like the identity outside Bryn. What does it mean? It just doesn't do anything there. What it does is it does here, yes? So let me take this kind of observable, because that's the kind of observable that we really probe in our experiment, and let me compute its correlation function. So O psi, and now expectation value of O tensor identity with psi. Now, this is, think of this as a matrix. This is a matrix that looks like a long line horizontally. This thing here is like this is a matrix which has a single row. This is like a square matrix. This is a matrix that has a single column, yes? That's this side, yeah? But it's matrix, matrix, matrix. It happens to equal to a scalar number, but it's still a matrix. Now, if you have a scalar object which comes out of a product of matrices, then famously you can change the order of these things and call it a trace. So this is equal to the trace of psi OA tensor 1. All I have done is, because this is a number, I might as well write trace. Trace of the number 5 is 5, yes. But then the moment I have a trace of something, I can change the order cyclically. So I wrote it this way. And when I write it this way, I'm taking the trace really over 2 pieces of this calculation, over A, the lab, and the environment. I can do the trace over the environment first. But the environment, this is environment, yes. But the environment, our observable, acts as the identity of the environment. It doesn't make anything. So in fact, what happens is that I get an object which looks like trace over the environment of psi. And this new thing is like an object that I can prepare ahead of time and only then multiply it by OA and form the trace. This is an allowed operation I just did here. So in the end, our calculation looks like the trace of OA times some new thing called rho A, and rho A is equal to this. This thing is called the reduced density matrix on A. And in general, the state that I started from, the psi, could be a pure state, but this thing will in general be a mixed state. And it's a mixed state because our state was entangled with the environment. If our state was not entangled with the environment, then this would still be the way for a state this would still be pure. The reason why it becomes mixed is that we have to forget about what exactly is entangled with us when we're doing this calculation. And the forgetting happens when we're doing the trace. So this operation of forgetting about the environment is called the procedure of computing the reduced density matrix. Now, the moment I have this reduced density matrix, I can compute its von Neumann entropy, which is minus log rho A log rho A. This is a famous definition of entropy. It looks the same kind of as Shannon entropy, but this is called von Neumann entropy because you have this operator here. But anyway, it's an entropy. And this number here is equal to 0 if your state, the state you get here is pure, and that means you weren't even entangled with the environment. If you are entangled with the environment, then this thing will not be pure, and then this number will not be 0. So this number is a measure of just how much entanglement, quantum entanglement there is between our lab and the rest of the universe, yes? So it's an entanglement measure. So now we come back to the ADS-CFT correspondence. Think of, I said, focus on a subset of these spins, like this one. Think of this as your lab. Now there's a question, is your lab entangled with the rest of this wave function or not? And what and you can compute it by computing this rho A, computing this entropy, and it's a number at the end. It turns out that that number is equal to the area of the surface through the bulk, through the interior of this network that separates it between here and here. You can sort of see how this would look like in this example. Here is our system, and you can say, what is like an area that separates this spins from the rest of the spins? So you can say, oh, it's the smallest possible area we're looking for. Well, I know how to find the smallest area. Just cut this line and this line and this line. This is the smallest possible cut that I can make through the network that separates these spins from the rest of the spins. This is a tensor network analog of that statement. And it turns out that these minimal cuts through tensor networks play the same role as areas in a spacetime. And this is what we learned from the Ryutake and Agi proposal in 2006. And this is the most fundamental thing that we could possibly hope to learn about quantum gravity, if it's general. It's certainly true in ADS-CFT. Now, why is it the most fundamental? Think about how you think about gravity, yes? In the beginning, what we learn about gravity is like F equals ma, okay? That kind of experiment. But later, what we learn is that maybe not everyone has learned here from the Mahasiswa Satu, but what we learn is that phenomena such as this and planets going around us in the solar system, and really everything about gravity as we know it, including black holes, is described not so much by forces. Force is just an effective description of something else, which is that space and time together are curved. So when I do this experiment, I don't want to do it anymore, but you know, there is a parabola that will happen if I flip this, yes? That parabola doesn't look like a straight line. But when you also include the time dependence, yes? Imagine a 4-dimensional picture where there's a 3-dimensional trajectory and a 4th time, then the then the parabolic motion in space and the motion in time together would actually make a straight line. And that's the proper description of gravity. And so gravity is not so much about forces, it's more about how space and time together are curved, yes? So that's what we learned from Einstein. General relativity is about the curvature of space-time. And what we call gravity is how space and time are curved. Now, as space and time curve together, think about those areas that separate one part of the exterior to the other, yes? If I curve it up a little bit, then this area will change, yes? But knowing about this curvature is knowing everything about gravity. So really, the areas are a measure of how space and time is curved, but that's all that underlies every gravitational experiment. So if we just knew about those areas, maybe we could know all there is about gravity. But Ryuta Kayanagi told us those areas are just entanglement entropies. So it suggests that everything about gravity is really about entanglement. And to study a quantum theory of gravity, I should just study this picture in detail. Okay, so this is the reason why I went into studying tensor networks, because I really want to learn about gravity, but this logic that gravity is just about curvature of spacetime. You give me a spacetime and curve it, then the areas, the minimal areas always register that. So I can learn about the curvature through the areas, but the areas are entanglement measures. So really, it's just about the entanglement. That logic suggests that everything about gravity is really about the quantum entanglement of the degrees of freedom that give me the dual description, the conformal field theory description, this description, the tensor network description. So it's all about entanglement there that tells us about gravity. So that's the reason why I study this question. And so this talk was going to be about some extra facts that you can derive about entanglement in states that describe spacetimes like that. But it's already it's 2:50. I have 8 minutes until but I guess I'm going to take some time from the question part to really show you a little bit about the actual talk. Is that a good plan? Okay, in the meantime, are there any questions? Because I've been talking for a long time. So if there are no questions, but was there a question? If there are no questions, then let me give you a brief, let's take a look at it.
Sorry,
yeah.
There is a question from the meeting.
Please.
How do we describe evolution and measurement in a tensor network state?
There is a technical answer to this question, which is that the time evolution operator, basically a path-ordered exponential of the Hamiltonian, there is a standard procedure for how to write it also in tensor network form, and you just combine, glue this tensor network to the time evolution to get a new thing. That formal procedure is called Suzuki-Trotter decomposition, or people call it trotterization, but any more detail would be too much technical for this, but that's the answer. Any other questions? Okay, so good. I just spent the last 54 minutes trying to tell you basically one single fact, which is that at least the quantum theory of gravity that we understand best can be understood using tensor networks. Okay, so far so good. And a key thing in it is that the most interesting thing about the geometry of spacetime, which is areas, are like minimal cuts through a tensor network. Now that it isn't exactly true that if I compute this quantity, this entropy of a subsystem, then it's literally proportional to the cut here. But if you remember, we talked about how the description offered by tensor networks gets better and better if I increase the bond dimension, the dimension of the interior bonds. So this statement also becomes truer and truer. If I take this tensor network and make the bond dimension larger and larger, then the actual entanglement entropy of a subsystem will be better and better approximated by just counting how many things I have to cut here through this thing. And I'm always looking for a minimal cut. On the real ADS-CFT correspondence, not the tensor network time model, but in the real thing, the entropy here is given by the minimal area. It's not just some area, but it's always the smallest area that we're looking for to find the entanglement entropy. So clearly, minimality in describing, is that a question, Sarah? Well, here the minimal cut is just, I mean, I'm looking for every way of cutting these spins from the other spins. And if I go like this, then I will cut too many lines. The smallest number here is 3 in this example. I'm just looking for the smallest number. And yeah, so clearly minimality is an important thing. It's definitely very important in the ADS-CFT correspondence, even if you didn't care about the ADS-CFT correspondence in tensor networks themselves. If I make the bond dimension large enough, then it will be true that von Neumann entropies are just minimal cuts. Yes. Okay. So this talk is meant to be about the class of quantum states which have a description where entropies are really equal to minimal cuts. But like I told you, it's not guaranteed to be true. It happens to be true when I make the bond dimension large. It happens to be true in the ADS-CFT correspondence, but it's not true in all states. So the fact that this is not true in all states, but it is true in quantum gravity, suggests that the minimal cut prescription is some fundamental feature of gravity that distinguishes gravity from other physical systems. So a person like me, who is interested in gravity, thinks of this as an opportunity. This is a chance to learn what is special about gravity. Why is gravity harder to study than quantum electrodynamics? It's definitely harder, but it's kind of hard to say why. Maybe this is one reason. So we want to learn whenever we can what is special about gravity, and that's one thing that really is special. And so in this talk, I'm taking that fact that the minimal cut prescription for computing von Neumann entropies is not something that is true in all of quantum mechanics, but it is true in ADS-CFT. And I want to learn more about when is it true. And I'm hoping that in that way, I will learn something about gravity. This is the idea of this talk. Okay. Now, this is a slide in which I tell you that the minimal cut prescription automatically implies facts about these entropies. And what we're going to learn here in this example is that there is about a relation of this type. That if I compute this von Neumann entropy, this quantity, yes, for some region, for some subsystem A, remember we're doing it for subsystems, like this is one subsystem, or on the previous slide, this was a subsystem and this is a subsystem. Give them names. This is called A, this is called B now, yes? But I can also take A, B together and compute the entanglement of that. So this, what we're going to learn in the next in the next 1 minute is that when I compute this entanglement entropy for a region A and B, and for AB combined, there is always an inequality like that. This is called subadditivity of entanglement entropy. And why is that true? Because remember, this is a minimal cut prescription. So suppose that I take this region A, I ask, what is the minimal cut? And I'm kind of doing what I did here. Imagine that there is some tensor network and I'm just looking for the smallest number of legs to cut to separate A from the rest. And so a picture like this looks like this now. You understand that this red thing here is supposed to describe this cut that I made over here. Yeah? So here is a cut for A, and here is a cut for B, the red and green. And now I want to make the cut for AB together. And a priori I have infinitely many possibilities, but in practice I just have 2 possibilities. I can reuse the cut for A and B together. I mean, a cut that cut A and a cut that cut B together make a cut that does the job for AB. But maybe there is another cut. I drew it in purple. It's another option, yes? And I'm always looking for the minimum. So I have a minimum over some number of options. One option is just the red thing and the green thing. But the red thing and the green thing is SA plus SB. Or I have the other candidate, and I'm looking for the minimum. And I have two options. Either it's going to be SA plus SB, but in that case, the inequality is true because it's equal. Or the purple thing will win because it will be smaller. But if it's smaller, then it's smaller. So again, this is true. You see, it's never possible that this would be bigger than that because this was a minimum over options which already included this plus that. Yes? And so that's the logic of why the moment I have this minimality, it automatically implies some facts about those entropies. Does that make sense? Now, this specific fact, which is called subadditivity of entanglement entropy, is a general fact about quantum mechanics. So this doesn't help me to distinguish quantum gravity from other systems. But it turns out that I can make a very similar argument, only more sophisticated, more complicated, the same kind of thing, and derive many, many more relations of this type. And those relations are not true in quantum mechanics in general, they're only true in gravity. So those relations are necessary conditions to describe quantum gravity. Does that make sense what I'm doing, what I will be doing? So I will be interested in arguments like this one, but not the same, it's similar. And those arguments will derive for us things like this one, but way more complicated. You will see in a moment. And those things are special features of quantum gravity. That's what we will be doing. So now let me show you what those things really look like. I'm going to skip this slide. They look like this. These are the kinds of things that you can derive using that. So I want to ask you, are you, I usually, when I give a talk about this, I usually ask a question, are you more impressed or are you more disappointed when you look at this table? How many people are impressed by this table? Nobody is raising your hand. You're very critical people. How many people are disappointed? Yeah, wow, yeah, I'm glad that we have the same. I mean, I work on this stuff, so maybe I should be sad, but I'm actually completely with you on that. So, yeah, so depending on your perspective, some people sometimes say that they are impressed. It is kind of impressive that humans, like, you know, people like you and me are actually able to derive things like this one. Imagine making an argument like this one about you have various options and either it's the same or one is smaller. That's kind of the argument, yes? Imagine making an argument like this for this thing, yes? That would really be something, yes? And yet we are able to do it. And so in some sense, it's impressive. But then it's also disappointing because you would like to look at this table and say to yourself, so that's special about gravity. But you really can't do it with this. The only thing you can say is, what's special is 3 times SAB plus 3 times SABD, blah, 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 equals bigger. That's not really the lesson that we wanted to learn. And so ideally, we would like to learn some qualitative lesson about gravity, but what we got with this is this. So we would like to, and it's worse, because I made this slide more than a year ago, and at that time, this is all that was known. But later, these people, and he's my postdoc now, but he was working with other people at the time. Later, these people did like a numerical analysis and found 1,866 other things like that. Okay, so now it's completely hopeless in terms of understanding qualitatively what's going on. Okay, so clearly, these are some really messy facts, and we should ask ourselves the question, are these facts meaningful or are they random in the sense that there had to be some conditions and they happen to just be these conditions, but there's nothing deeper in there. Or maybe these things really have a meaning. And so is there a framework to organize it? And does it tell me something new about the ADS-CFT correspondence that I didn't already know? Now, this last question is kind of hard for me to convey because I understand that for most of you, I just told you about the ADS-CFT correspondence for the first time. But imagine that you have worked on it for the last 15 years or 20 years, like I have. Then you look at this table. Am I really learning something new or nothing new? Yes. Maybe for you, everything is new right now. So you might think, this table is really important for ADS-CFT. A priori it isn't, but we would like to be able to say that it is. So is it really? Okay. So clearly we need to have some new perspective to make progress on this question. So what my student Sirve and I thought about is that we wanted to look at this table and we wanted to extract some real insight out of this table. And one reason why this is hard is that there's just so much like combinatorially complex data in the table. We have to keep track of these like ABC, ABD, AB, various like combinations of regions. Yeah, and maybe a computer can do it in the era of like artificial intelligence. Maybe for the AI it's not harder, yes, but for you and me it's hard to really understand what's going on here, just because we can't keep track of the indices all at the same time. So maybe we could do something so that we can forget about those indices. And here's what we can do, which is that we can just track of how many regions there are in every term. And the reason why this is a meaningful thing to do is that you have these inequalities. Imagine that you have a system that has a large number of constituents like A, B, C, D, F, G, yes? And you have one inequality like this one, but then you can just relabel A, B, and C and act with the permutation group on the labels. The permuted labels will also satisfy the same type of inequalities. So imagine taking one of these inequalities and acting with the permutation group in every possible way. It generates for you all of these various inequalities, yes? Like for example, just to be clear what we're talking about, let's take the example that we had before. The subadditivity was A plus B is greater than or equal to AB, yes? But imagine that you have A, B, and C together. Then you can permute A and C as well, and you will have C and B is greater than or equal to CB. And then you can permute B into C, and you will have A plus C is greater than or equal to AC. You have one inequality, but you really have three because you can act of the permutation group on it, yes? Now what we're doing is taking all of them and adding them up, yes? Take a sum of all of them. And what's going to happen when I take a sum? I'm going to have A plus B and B plus C and A plus C. By design, every one of these terms, A, B, and C, is going to show up the same number of times, yes? What about here? I have pairs, AB, BC, and CA. Every pair shows up the same number of times. So clearly, what will happen is that by adding up all permutations, I am forgetting the details about what region goes where. I'm only keeping track of how many regions there were in every term. And that's the kind of inequality I get if I add up all the permutations. So here's an explicit example that we can look at. Take this inequality over here. I copied it for you there. And you can and what I have defined is a new piece of notation. The average of all of those entanglement entropes that have three regions in them, like ABC or ABD. And here's the average of all things that have two regions in them. And here is the average of all things that have four regions in them. So this is my new notation. These SPs are averages of p-partite regions entropies. And then what I'm saying is that you start from this inequality, do like what we did over there, add up all permutations, divide by some normalization, and what will happen is that you will get an inequality of this type. And why is it that? Because there are 8 terms here, I shaded them, which have 3 constituents in them. In fact, there are 9 on the left and 1 on the right, so it's 9 minus 1, which is 8. And then, why do I have 6 copies of S2? Because there are 6 things shaded in yellow, which have 2 things in them. And why do I have 3 times S4? It's because I have 3 things that have 4 things in them, 4 regions in them. So this inequality, by doing what we did over there, yeah, adding up all permutations, automatically gives me something like that. Now that's something that I should be able to understand by human thought without AI, right? Okay, so what we're going to do now is we're going to apply this kind of procedure, take this into that, just go to the averages. So forget the indices, but just go to the averages. We're going to do it for every one of the inequalities in this table. And that's what happens. Look what happens. There's only one inequality that you get out of that. And I hope that, so a moment ago I asked you, are you impressed or are you disappointed? Are you impressed or are you disappointed? Because you should be impressed that there's all this like junk of data. It looks so ugly, but when you do this simple procedure, that suddenly it becomes so simple and there's just one thing. So I would say, as a physicist, this must have a meaning. When you look at the previous table, it's perfectly possible that this table is just total mathematical junk. Like maybe there is nothing in there. But the moment you land on this kind of thing, then you know there must be an explanation. And so my next goal is to tell you about that explanation, like why this and what does this really tell me. This is supposed to tell me something special about gravity. So this is not, this inequality is not true for all states in quantum mechanics, but it's only true for states that describe gravitational spacetimes, that satisfy the minimal cut prescription from Luther-Kanak. Okay. So yeah, so this thing is actually an example of that one when P is equal to 3. Okay, so what does it mean physically? So to study what this means physically, we're going to ask, so when you have an inequality, then generally the most interesting thing about an inequality is how you get as close to breaking it as possible. In other words, when you saturate the inequality. If I make the two parts equal to each other. Sorry, can I say one more thing about this? Why I find this exciting? So if I go back, think to, so this is also, this inequality is also true for tensor networks, yes? But to design for tensor network states that have a large Baum dimension. But tensor networks are like this thing that we drew here, yes? So if you are a mathematician, you didn't have to know any of this physics. That's why I said to some people during lunch today that you actually don't have to know any physics to start doing research on this thing, because you can just draw the graphs, okay? So if you just draw the graphs and look for minimal cuts, this thing will still be true. And so think of this not necessarily as a fact about, it is a fact about a necessary condition for a quantum state to describe gravity. But if we take a step back and think about it more abstractly, this is really a theorem in graph theory. It says no matter how you draw your graph, you can draw this kind of graph, that kind of graph, or any graph, this statement will always be true about the minimal cuts, yes? So usually as physicists, we're used to the idea, unless you're like Edward Witten, okay, who wins field medals. But modulo that, we're used to the idea that when we need some mathematics, there is already a mathematician who did it for us. Typically, we're behind, and the physicists are ahead. But this is an example where I have talked to a lot of graph theory friends, and because my student and I, Survey, we conjectured this thing, and we couldn't prove it for a long time. We prove it now, but for a long time we couldn't. And when we were at the stage when we couldn't prove it, then I kept going around asking my graph theory friends, mathematicians who work in graph theory, is there a theorem like that? Or would you know how to prove it because you're a graph theory specialist? And the answers were no and no. So we proved it in the end. So I just want to say my student and I actually proved a new theorem in graph theory because we needed this even for this purpose, which I think is kind of cool. Yeah.
What is SP again?
It's the average of the cuts that you make when there are p parties on one side and n minus p on the other side. It's the average. Yeah. So it's kind of remarkable that there is a statement of that type, that the average cut that separates p things from the rest, and the average cut that separates p minus 1 things from the rest, and p plus 1 things from the rest, that these things always have to obey this kind of relationship, that they do. Okay, so now, back to analyzing this from a physicist point of view. So because we're interested in this, we would like to understand what really this tells us. And when you have an inequality and you want to understand it, then the most natural thing to do is to try to break it. As in, like, go to saturation and see if you can make those things equal to each other. Yeah. You can even try harder. I mean, try not just to make it equal, try to make the right-hand side bigger than the left-hand side. Then you would prove that your thing is wrong, but that's what we do in science. We try to falsify, yes? So you try to falsify. But in practice, you won't be able to falsify. You might as well make it equal, yes? So you try to make it equal, and then you realize, after you study this thing for a while, there are basically two ways to make the two sides equal. One is this, and the other one is that, where the entropies of p-partite regions have a scaling as a function of p that's proportional to p, or proportional to a quadratic which has a minus p squared in it. I wrote it as p times n minus p for some reason, yeah. And let's think about what these two things mean. So here I attached some names to them. But if you don't have if you haven't been reading papers about this subject, that these names won't mean much to you. Perfect tensor name, for instance. But let me give you a flavor of what this really means. Do you remember our argument for why A plus B is always bigger than AB? It was that you had the surface for A, you had the surface for B, and then you were looking for some surface for AB, yes? But maybe you could just reuse the surface for A and B together, yes? Okay. Now, okay. So suppose that you could reuse the surface. Suppose that A plus B was really equal to AB, yeah? That means that looking for a minimal surface when you combine things, A and B combined, versus doing it separately for A and separately for B makes no difference. You always get the same answer, yes? So in other words, if you think about the entropy, yes, then A has some entropy, B has some entropy, AB has exactly the sum of those two entropies. What happens when you're not equal? Yes, suppose that it's bigger. That means that A, B together have a little less entropy than A separately plus B separately, yes? So the question is entropy extensive or is entropy not extensive, yes? And what I'm saying is that this regime is when the entropy is extensive. When the entropy is extensive, that means that we go to larger and larger regions. We don't have to look for further minimal cuts. We just take the initial minimal cut for A, B, and C separately, and we will just reuse them for A, B, AC, ABC, and so on. Yeah, that was the idea there, yes? So if we can always just reuse the same cut, that means that combining regions has no effect. But if you find that combining regions has some effect, then you cannot reuse the same surfaces, then this will no longer be true, yes? So it turns out that the degree to which we can reuse the same surfaces is called mutual information. And here I'm saying nothing has mutual information with anything. But nothing has mutual information with anything basically means that the problem decouples. It's the simplest possible thing. You have a problem for A, problem for B, problem for C, and then you combine them into A, B, A, C, A, B, C, A, B, C, D, and so on. You just reuse it. It's the most boring thing that can happen. And that's what it is. So nothing has mutual information with anything. That's this behavior. And if you plug it in there, you see that it saturates it. Yeah.
But it's in the same dimension.
Here we're assuming that they're in the. Yeah. Although this is very abstract, so you could imagine. Yeah, probably you can cook up a setup where they wouldn't even be in the same dimension. Probably. This one is more interesting. So there's more than one way to saturate it. The other way to saturate it is with a quadratic. And what I want to tell you is that this quadratic has a very special form. I mean, it's a very special thing. That quadratic means that the system has what's called bipartite entanglement. Everything, it's like entanglement when we hold hands together. I hold your hand and she holds his hand and so on, yes? It's not, there are no like triple or quadruple or some other arrangements, yeah? And that's what this bipartite entanglement is. So let me explain why that's true. So here is a picture where you have a tensor network which has only bipartite entanglement. So it's not like this tensor network, but it's some other tensor network. And the fact that this has only bipartite entanglement in this tensor network is expressed with the idea that there are no interior tensors. Everything is an exterior tensor. Like everything is on the outside. There's nothing on the inside. Like here, there is this node here. It's on the inside. Over there, there's nothing on the inside, only outside, yes? So that's bipartite entanglement. And I want to say that when you compute the entanglement entropies of p-partite regions in this setup, then you will get something which is proportional to this quadratic. And why is this true? Well, suppose that you wanted to compute the entropy of a specific p-partite region. That you would take your p things and your n minus p things on the outside, and then you would say, how many legs cross it? Remember, we're looking for a minimal set of legs, yes? So, I don't know, we can count how many things there are here. But imagine doing it now for every set of p things, yes? If you do it for every set of p things, then the answer is only going to depend on how many legs there are to cut altogether in the whole thing. So we can define a quantity, which I call S star here, which is take the number of legs that you have here and divide it by n choose 2, n times n minus 1 over 2. The number of possible connections, yes? You have a number of possible connections, like here I have 1, 2, 3, 4, 5, 6, 7, 14 things, yes? That means that there are 14 times 13 over 2, which I believe is 91 different ways of combining one thing with another. And then I have some number of legs here. Take the number of legs divided by 91, by 14 times 13 over 2, and then you will get the average number of legs per connection, yes? Clearly, when you compute the average entropy of a p-partite region, then what you are doing is you're always counting how many connections there are between these p and those n minus p, yes? P, on average, what you will get is p times n minus p times the number we got before. And so that's the reason why it has to be proportional to that quadratic. The average entropy is this. So maybe you didn't follow the details of this argument, but it's a fact and it's not hard to see. And so in the end, what we see is that this boxed inequality that we are so proud of, there are two ways to saturate it. One is a boring way. Nothing knows about anything. It's all independent things. And the other one is when everything has a direct counterpart and the entanglement is kind of the simplest possible. It's always like me and you and her, yes? There is no tripartite entanglement. So sometimes we call this kind of thing that it saturates the monogamy of mutual information. Monogamy is the idea that like you don't have like marriages between 3 people or 4 people. It's just between. So anyway, okay. So there are two ways of doing. So there are two ways of saturating this thing. So now one is linear and one is quadratic. Now let me draw this quantity SP as a function of P, and one extra thing comes out of this fact. Says that if I want to extremize this inequality, suppose that I want to extremize it not just for one value of P, but for all possible values of P. So make things as extreme as possible. It saturates not just one of these inequalities, but it saturates it for P equals 2, P equals 3, P equals 4, P equals 5, for all values of P. And it turns out that that is possible essentially in only one way, which is that you go linear for a while, and then you will go quadratic for a while. You cannot, I told you that there are these two modes of saturating it, but you cannot go back and forth between them. You cannot go like linear for a while, quadratic, and then linear and quadratic again. It's linear up to a point, and then quadratic after a point. That's the only way to do it. I don't have time to show you why that's true, but it turns out to be true. So then, there is a new parameter, which is a special value of P prime, where the linear becomes the quadratic. And what is that? Does this have a meaning? Because remember, we're doing this analysis because we are hoping that we will learn something fundamental about gravity by taking these inequalities. So I told you that we found the inequalities because we're looking for something special about gravity. But now we're studying the inequalities, and we're finding that the most extreme form of entanglement that is allowed by the inequalities is one that goes like linear up to a while and quadratic after that. And there is a special crossover called P prime. What is the meaning of that P prime? It should have some meaning in gravity, right? And so let me tell you. It is the age of an evaporating black hole. And the most extreme forms of entanglement that are allowed by this are actually intermediate stages in the process of black hole evaporation. And the value of P star is like the age of the black hole. So I could keep going and tell you sort of more about this fact, but maybe this is the right time to like stop and then see what questions you have. And maybe this is a good place where I can give you a motivational spiel, which is, would you like to learn more about it? Read my papers and read many other papers that I cite. Read papers that I didn't cite as well. Yes. And there's a lot of stuff like that. And if you need if you would like to get into this line of research and you want guidance for like what papers should I read first so that I get into it, then just ask me and I will tell you. Go and learn about it on your own. Maybe that's the last thing. Yeah, thank you.
Now, normal time actually we have 5 minutes, but we can extend up to
No problem.
30 minutes. So, is there any questions? Ada pertanyaan? Silakan dari audiens.
Minimum area and build material di theorem. Is it only works in area CFT and CFT things, or does it work generally in quantum states?
So it certainly doesn't work in general in quantum states, but the question doesn't even apply to general quantum states, because a general quantum state doesn't have some additional description like a tensor network with some properties of the tensors, or a space-time or something. There is nothing to apply the minimal cut prescription for a general state. Now, if I go away from the usual, so yes, so the answer is no, it doesn't apply in general, but the question doesn't even apply. But even the question doesn't apply in general, not just the answer. Okay, but if the question is, if I go away from the usual ADS-CFT setup, are there also situations when this applies? And so I would mention like at least 3. Yeah, one is what's called the random tensor network states. So if you didn't know anything about, if you just didn't care about gravity, and you started drawing pictures like these ones, and remember every time you have a node, it's erased over here, but every time you have a node, it represents some tensor with some indices, yes? If you chose those tensors randomly with Haar measure, then unless your bond dimension is very small, but already at bond dimension like 6, it already becomes approximately very true. So it's a very good approximation that the minimal cut prescription works. So a minimal cut prescription works for tensor network states where the tensors are random, and the bond dimension is like bigger than 5. Then it's enough. The next thing is that it applies for other theories of gravity that are not part of ADS-CFT in any usual sense. So it applies, for example, to the SYK model, which is not of the SYK variety. That's a duality between 2-dimensional theory of gravity and a 0 plus 1 dimensional system. Then it applies to something called warped ADS, warped CFT, which is like ADS CFT, but the structure is very different. It just has different symmetries, so it's not a conformal field there on the CFT side. Yeah, so there are lots of places where it applies in some form or another. So it seems to be a general fact about states that do have an extra description in terms of a one higher dimensional object. That's what I would say. Oh yes, so there's the question is, if not Mera, are there other tensor networks that also work for ADS-CFT? And the answer is definitely yes. And the most famous example is called the HAPPY network. It's called HAPPY because of the names of the people who authored it: Harlow, Postavsky, Preskill, Yoshida. HAPPY. And so that's one example. There is in fact, my work is In fact, I have papers where I argue that, in fact, the connection between MERA and ADS is kind of wrong. So at the level of this presentation here, it's a very good example. But if you look into the details, then actually a lot of things are not quite the same. So, the picture is more subtle, and there are many other tensor networks. Oh, there is a very important tensor network called I forgot the name of it, but by a guy named Glenn Evenly. Okay, but if you want more details, then I'll tell you more details. But there are other tensor networks for sure.
Ya, apakah tensor network yang lain juga memberikan interface atau kita bisa punya network?
Oh yeah, there is a So do we also use the minimal cut in other tensor networks? And even more so. So actually, to the extent to which there is a problem in relating this tensor network to ADS, there is let me tell you one problem. One problem that shows up here, which I pointed out in one of my papers like 10 years ago, is that, so remember in ADS, this cut should look like this, yes? And the key thing is that the symmetries of ADS are such that this point is the same as this point and this point. It looks like this point is deeper than this one, and this point, like this point is deepest kind of, and this one is less deep and this one is less deep. But this is just the way we draw it. But there are symmetries that can take this point to here. And so in fact, all of these points are the same in terms of symmetry. But here it's not like that, because that place is very different from this place. Here it is really objectively true that this place is deepest and this thing is less deep and this thing is less deep. So this place is special for this cut, whereas here there is no special place in that cut. So so that's kind of the biggest problem in relating the MERA network to ADS. And then these other tensor networks that I told you about actually help with that problem. So they will not have that problem. So they will apply the Ryutaka and the minimal cut prescription, but they will apply it even better, like in more detail. Okay, other questions?
Ya, saya ingin mencoba membuka grafik dengan strongly correlated system di connected matter physics. For example, in fractional quantum states, where electrons are condensed in a certain magic way number.
Yeah.
Saya penasaran apakah minimal cut juga bisa menjelaskan magic number yang di
Okay, so so this is it's not my area of expertise, but I am not aware of any work that would actually relate the special fractional numbers to that. There is definitely a lot of so not at this level, but it's definitely helpful for that problem too, because the first thing that we typically say when we study any quantum, any Hall effect, in fact, even before fractional, yes, is that gauge degrees of freedom become physical when there is in the presence of a boundary. It's like an important first step in studying the Hall effect. And so tensor networks are a realization of that fact. So here is one way in which they are useful for thinking about the whole problem. And we can see it right away. Why do we see that? Because remember when we're talking about the bond dimension here, I said here we know that the bond dimension has to be 2 because we're describing spins, so they're up and down. But here we don't know what the tensor network is because we're using we're summing over here, we're making a trace. We never explicitly have access to these degrees of freedom. So the bond dimension could be a bond dimension equal to 2 or 5 or 1,000,000. Yes, and yes, right? Okay. So the key thing is that what happens here, we do not see it. So now imagine that I temporarily broke this bond, yes? And then I'm gonna sort of draw it up to here and up to here, yes? This is the broken bond. And now imagine that I act with a unitary over here, this is U, and over here I act with a U dagger. So when I combine them, then this would be some kind of degree of freedom that's multiplied by U and U dagger. They will just cancel out, yes? Okay, so inside every closed tensor network like that, I can put a U and U dagger on this side, and then I can take this U and absorb it into a new vertex. Does that make sense? So I can take the old tensor and map it to a new tensor called old tensor times U. And this one will be called old tensor mapped to old tensor times U dagger on the left. Yes? What do we call the freedom of multiplying things by U and U dagger locally? We call it gauge symmetry. And so the statement is that every time you have a closed bond, there is always a gauge freedom in possibly multiplying it by U and U dagger on the two ends of the same bond. Yes. Now I have this freedom whenever I have a closed bond. But when there is an open bond, then I don't have that freedom. Here, multiplying things by U actually makes a physical difference. That's exactly the idea that gauge symmetry, in the presence of a physical boundary, becomes a physical degree of freedom. So tensor networks kind of incorporate that wisdom in the start. I don't know if that was any helpful for the question. I don't know if anywhere it actually goes to the values of the special fractions in fractional quantum Hall effect, just like the overall context where we have a gauge symmetry and a boundary. Yeah.
Apakah tadi apa minimal surface itu ada mulai bahwa monumen entropi itu bisa dilihat sebagai nilai minimum dari silent entropy.
So sorry, the von Neumann entropy can be viewed as a minimum over over all possible measurements of Shannon entropy. Actually, I didn't even know that fact, so I'm learning it from you now. So maybe we know that, and I don't know, but I don't. Why is okay, but why does this work for? Yeah, I mean, in some sense, this whole work is trying to understand that. So, but if you ask a broad, yeah, so. Okay. Yeah, so I don't really have a good answer to this question. In some sense, okay, so this argument that I gave you here is a statement that a bulk gauge symmetry becomes a global symmetry. Because when it acts not here but here, then it becomes a physical symmetry. So it's a global symmetry. So a bulk gauge symmetry is a boundary global symmetry, and that's a statement that's true about tensor networks, and it's also a statement about gravity. So maybe when you say why it works for gravity, we should really make this question more specific and say, why doesn't it work for some other favorite system that I have in mind? Then it will be easier to answer this question. Because of this, maybe a natural counterpart would be to say, can we define something like this for theories, for gauge theories that are not gravity? Like gravity is a gauge theory where gauge is diffeomorphism. So what if I had gauge theory like electrodynamics? Would I have an analog of this story in some sense? And I'm not aware of this. And if you ask me why don't I have similar statements applying to ordinary gauge theories, then I don't really know why. So that's like a statement, what makes, if I have the graviton as spin equals 2, but the photon of spin equals 1, where am I using the fact that graviton is spin equals 2 and not spin equals 1? And I'm not really sure where. So I don't really have an answer to that question. Yeah, so, but we're sort of trying to answer the question, what's special about gravity? But I don't really know how to relate it. Huh? So the question is like, does it have an error as an origin and d dimensions? But what's the question? Oh. So when different, okay, so the question is, I'm going to repeat it for everyone and also translate it. So the question is, what is a quantity that, I understood the question as being, what is a quantity that really motivated the introduction of this Mera tensor network that studies, from which we can learn like why Mera is useful. And I think the reason why that's the first thing that was really, there were two reasons why Mera was suggested. One reason was that it's called multi-scale entanglement renormalization ansatz. So it was really about the behavior of entanglement, yes? And the idea is that in here, there are some degrees of freedom which are entangled with everything else. But clearly, like, there is some entanglement which is sort of local here. And then when you go higher and higher in this picture, then we are talking about then the bond here and the bond here it's like if you had to cut it, then this would be part of some entanglement entropy, yes? But bonds that are higher are about entanglement at larger scales. Bonds that are lower are about entanglement between smaller scales. Like this bond here is about entanglement between here and here. This bond here is about the entanglement between here and there, because that's what I'm connecting. And so the idea of Mera was, can I draw a map of entanglement where about every place in the map you could say, this is entanglement between UV and UV. This is entanglement between IR and IR. And that's kind of what Vidal was trying to do. So that's why multi-scale entanglement renormalization ansatz. And if you ask, is there a quantity that really captures this? Then the quantity would be the von Neumann entropy of a single interval. And this famously, in the ground state of a conformal field theory in 1+1 dimensions, depends logarithmically on the size of the system. So there is a formula first discovered by Wilczek, the Nobel Prize winner, in 1995 or something. Which is that the entanglement entropy of this is equal to some number times the logarithm of this size, yes? You can see this logarithm because, like, if this was twice as big, then I would just have to go one extra layer and there would be one extra thing. So it really behaves logarithmic. 2 times bigger means 1 extra. 4 times bigger means 2 extra things. The quantity is the von Neumann entropy of a single interval.
Sorry, there is a question from Zoom. Can you discuss the effect of the defect to tensor networks?
Oh, I wrote a paper about it. So so I have I know that this is about a defect in a tensor network, but I tried to be funny, and the title of my paper was a defect in the interpretation of gravitational interpretation of tensor networks. So like the defect is in the CFT or the defect is in how we understand it. Yeah, I tried to make it ambiguous in the title. So please just read my paper.
Karena kita bisa mempelajari evaporasi rumah kita, padahal tadi di inequality-nya kita ada.
Yeah, so you have it's like in the thank you. The question is how do we really see the age of an evaporating black hole here? So the thing is that there is so I would have to talk more about the how we describe the process of evaporating black holes, but there is something called, there are influential papers that were written by Ph.D. in the 90s, and then there is a very influential series of recent papers from like 4 years ago about islands. How many people have heard about the island program for and replica what's called the replica wormholes for understanding black hole evaporation? Yes. So both Page's work from the 90s and the replica wormholes / island program from 5 years ago. I mean, it's ongoing. Started 5 years ago. All of them have a certain common feature. And if you take that common feature and try to draw that feature in the form of a tensor network, then you can do it. And then you compute in that tensor network those entropies, and it turns out that they just have this kind of behavior. Yeah. So that's all I'm going to say for now. So the idea is you take those models of black hole evaporation from Don Page and from islands / replica wormholes, and you try to ask yourself, if I wanted to draw the same conclusions using a tensor network, what kind of tensor network would I get? The answer is that you would get a tensor network like this, where there's just a single star with many legs, but some number of legs have been combined into one big leg. And then in that context, when you compute those entropies, they become just like that. And so the models give you this. That's the short answer.
Just to follow up from the previous question, so is it a real black hole or just graph black hole? I mean, is it a model or is it a toy model or a real black hole?
No, we definitely mean a real black hole, but there are a lot of buts. So let me be specific about that. The first one is that we are assuming asymptotically ADS boundary conditions, and we believe that this is only so we have calculational control, and we're not losing some detailed information about it, about the black hole. But this is subject to questions. So that's the first thing. The second thing is that there's a technical thing that's done here in those island models, where you imagine that somebody is out of an evaporating black hole. It's constantly catching that radiation and registering it. And there is that's what you kind of have to assume. There is nothing wrong with that assumption a priori, but there is an influential physicist from India, Subrat Raju, and he's not the only one, but he's most famous for it, who argues that the moment you have a person who is really capturing all of this radiation, that person will automatically back react so strongly that the picture changes, and then who knows, maybe the black hole isn't evaporating anymore, or we're not really talking about proper gravity anymore. So there is a question of, can we really manipulate the radiation in the way that is stipulated here? So I would say that there are these two big questions before we can say, oh yeah, these are the real black holes. So the intention is that this is supposed to be describing black holes like we know them, but there are two caveats, and these are the two: ADS boundary conditions and the fact that we have to imagine that someone captured all that radiation and controls it in one place. And that amount of control might just totally break gravity anyway.
As this tensor network is also applicable for system like the spacetime.
Oh, this is a subject of like an ongoing flurry of papers. So I don't want to adjudicate and say these papers are right or wrong, but a lot of papers are being written about this right now. There's probably one today. So yeah, that's something that is being discussed currently, and there's no consensus on it. So I'm gonna just make a brief announcement, which is that 2 days from now, so today is Tuesday, so on Thursday, I will be giving a talk at Ph.D, and it will be online. And in that talk, I will talk mostly about differential entropy, which is similar but different to this subject, and it's very closely related. So if you're actually interested in this, then it might be beneficial to hear both talks together. There will be almost zero overlap between the two talks, except like where I talk about the backgrounds to get the talk started. I think at Ph.D I will make my background shorter than 1 hour, not like here. But if you're interested in learning more about a related set of things, then 2 days from now, yeah, Ph.D and online. So let's finish here. Thank you very much.
So that's thanks for
Really, thank you very much for your talk. But give you something which probably Bustela already has this placard, but I'm sure that the mark she doesn't have. So this is the mark and Parman design. Yeah, so
Oh, this is fantastic. Thank you very much.
Right.
And quantum coming in, there is a Schrödinger sky.
Right. So this is the IQ and for the Indonesian quantum initiative.
Wonderful. Thank you very much.
Thank you. Thank you.